Hi, I'm Dima. Today I talk about deterministic finite automata and code control flow obfuscation. It's not a theoretical presentation, I will show you some real obfuscated code found into the wild. To be honest, I'm not good in non-technical talks, so let me skip my self-presentation, introduction, funny jokes. Let's start right from the technical things. I found this code in an iOS application from App Store. The code is a part of anti-tampering protection. At first, it doesn't look any special. It's an Objective-C method, the class is device UID, the selector is safe. The code itself looks absolutely ordinary, but if I try to execute it till an exit point, till a return instruction, on a jailbroken iPhone, the application process just exits. Boom. Okay, let's take a close look at the code. Respawn the application under LLDB, then breakpoint and disassemble the Objective-C method. That's how the method code looks like. Please note that instruction addresses are different now because of ASLR on iOS. Well, first of all, the epilogue instructions look weird. They do not balance stack, there is no return instruction. And there are two more pieces of weird code related to the epilogue. Now you can see all instructions of the weird code in the right part of the screen. Of course, there are no labels in the original machine code, but I replaced absolute instruction addresses with labels to make the code more looking like an assembly sources. I will explain the label names in a couple minutes. Now let me explain how the code works. First of all, it calculates the address of, well, let's call it some data for now, and store the address in the general purpose register x23. Then the code sets some stack variable to 0. After that, the code checks if the stack variable value is in range from 0 to 17. The 17 is in hexadecimal number system. If the variable is out of the range, the code falls into an infinite loop. From my point of view, it's a strange way to handle out of range errors. The last piece of code is quite important. It explains actually everything. Let me remember that the register x23 points to, we called it some data. Looking at the code, it's easy to see that some data is actually an array of 2 bytes unsigned integers. And the stack variable is an index. The code reads an element from the array by the index, multiplies the element by 4, and adds the result to the address of first instruction after the code. It's the base label on the slide. Finally, the code calls the resulting address. As you see, the array contains some offsets. However, the offsets are not byte offsets. An element of the array is not a count of bytes to add to the base. It's a count of IRM machine instructions you should skip moving down from the base. As you probably remember, every IRM instruction is 4 byte length. So the code reads an element of the array, then multiplies the element by 4 to get some byte offset, and then the code calculates some absolute address by adding the byte offset to the base. Well, I hope that the label names array adder, initial array index, and base I explain it now, and the weird code does not look too weird anymore. I will explain the dispatcher label name later. Okay, but there are two additional questions here. The first one is, what offsets are in the array? Now it's clear how to calculate absolute addresses from the offsets, but I'm too lazy to do it manually for every array element. So I created the custom LLDB command dump off. It finds the array in the virtual memory of the application process, loops array indexes, reads the elements for every index, and calculates the corresponding absolute address. Just to make sure that the array is dumped correctly, let's make an experiment. Breakpoint the branch instruction before the weird code is executed and continue the process. The breakpoint hits, the debugger prints tons of useless information, but I use the magic key combination cmd-l to remove it. Then I dump the register x9 and see what the address in the register equals to the Then I dump the register x9 and see that the address in the register equals to the address calculated from the very first element of the array. Okay, let's take a look at the code at the address. I step one machine instruction forward and use the magic cmd_l to clean up the step instruction output. Then I disassemble the code and check it. I see that the code does something useful. I do not try to understand what exactly, it doesn't matter now. Then the code stores a new index to the stack variable and branches to the dispatcher label in the virt code. Remember the dispatcher label? I promised to explain it later and I will. Well, I use the dump off command and randomly checked some addresses. The code at the addresses always works in the same way. Do something useful, store a new index to the stack variable, branch to the dispatcher label in the virt code. Well, now you understand how the virt code works, but let me explain it again without machine code, just in case. At the very beginning, the index is 0. Then the dispatcher code reads the corresponding offset from the array and calculates the absolute address. Then the dispatcher code calls the code at the address. The code does something useful, changes the index, and branches to the beginning of the dispatcher code. The dispatcher does the same trick again, this time with the new index, and then again and again and again. This obfuscation pattern makes static analysis of the code quite hard. The dynamic analysis is not so hard, but we anyway need to spend some time to understand how the pattern works. Okay, now let me know how it works. Now we know how it works and can trace the calls. Let's restart the application under LLDB again. All the addresses are different again because of ASLR, but I have the dump off command to dump the array and another custom command I created, the track flow, to track the dispatcher calls in real time. The green addresses is the currently called addresses. The red addresses is the previously called addresses. If you constantly see the same green address, you are looking at the loop. It will take about probably 10 seconds, and currently you are looking at the obfuscated calls to say in real time. Okay. As usual, the calls ended in process exit code, in some process exit code. After 158 calls, the process exits. Let's remember the index of the current call. It's E in hexadecimal system. Also, let's remember the index of the previous call. It's 3. Now I restart the application under LLDB again, dump the array, and disassemble the code at the address by index E. And here is the result. The code calls exit with the only argument 0. That is why the process exits. Now let's check the code at the address by index 3, because obviously this code told the dispatcher to call that exit code. Okay, I disassemble the code and see a system call. It calls the Pathconf function. Let's respawn the application under a debugging, breakpoint the service instruction, and dump the first argument of the Pathconf function. It's a path to a drop beer binary. Some jailbreaks install it to your iPhone, and some anti-tampering protection check for the binary. Okay, we completely understand the obfuscation pattern now, and it looks quite familiar. Is it a DFA? Let me remember what a DFA is. To define a deterministic finite automaton, also known as DFA, we need a finite set of states. Let's denote it by Q. A finite set of input symbols, an alphabet. Let's denote it by A. A transition function sigma that maps a state input symbol pair to the set of states. We also need a start state Q0 and a finite set of accepted states F. The set F should be a subset of Q. Further, an ordered set of input symbols is called a string. The DFA starts with the start state Q0. It takes input symbols from a string one by one and changes states according to the transition function. If the last step is an accepted one, we say that the DFA accepts the string. Otherwise, it rejects the string. There are many ways to define the transition function sigma. Probably the simplest one is state table. The table contains a resulting state for any state input symbol pair. Okay, now let's try to represent the dispatcher, the weird code, as a DFA. Let's define the set of states as follows. Let the start state Q0 be nothing is executed yet. Another states are defined as the code at some address is called by the dispatcher, or the code at some address is executing now. The alphabet is the set of the indexes from 0 to 17 in hexadecimal system. The transition function is defined by the state transition table on the slide. The table may look disappointing. You probably already noted that all rows within any single column are the same. From a mathematical point of view, the obfuscation pattern is quite simple. As we already noted before, the Q0 nothing is executed yet state is the start state. Finally, let's define the accepted states. Let any state be accepted, excluding the state the code which calls exit is executing. So we accept all states except the states, the code that calls actually that exit function. Okay, let's go back to the obfuscation pattern and consider it as a DFA. Here, the initial state is Q0. Nothing is executed yet. The string is unknown yet. We know only the first input symbol. It's the index 0. The dispatcher acts like a transition function. It takes the index, calculates the absolute address, and calls the address. From math point of view, it takes an input symbol and changes the state of the DFA accordingly to the transition table. Then the code does something useful and branches the dispatcher from another index. From mathematical point of view, the code just adds another input symbol to the string, so the transition function can change the state of the DFA again and again and again. Well, this means that our DFA accepts a string only on a non-jailbroken device. If the device is jailbroken, if your iPhone is jailbroken, the DFA does not accept the string, and we see that exit call. Okay, the idea of this code execution flow obfuscation is not new. I mean, it's not new at all. 20 years ago, 4 scientists published a paper. The title was An Approach to Obfuscation of Control Flow of Sequential Computer Programs. Wow. Let me read a couple words from the article. A control flow of a source program is grouped on a switch statement called a dispatcher, so that the targets of go-to jumps are determined dynamically. A dispatcher may be viewed as a deterministic finite state automaton, realizing the overall control over a flattened program. So now you understand why that weird code is called a dispatcher. 20 years ago, okay. Well, that's it. So it goes. Thanks for watching, and here is my email if you want to ask me something. Well, see you.
Do we have any questions from the audience? Let me check. We really need to get some questions. Do we have any questions, people? Please bring back some hope, some faith in humanity. Anyone here? possesses technical knowledge to shape a question to our speaker? Okay.
Well, I should say it's a quite specific area where
Of course.
you're doing reverse engineering and you're doing math at the same time. So it's maybe a little bit hard to get it, for 15 minutes. I understand it may be hard, but this is what I do and this is how it works.
Yeah, it does, and it certainly needs some practical background to consume that. But we still want to have practical and hardcore technical talks on the conference program. So yeah, I just hope there are questions.
Yeah, I'm ready to answer. I'm here.
Let's give it another couple of minutes.
Okay.
How is business overall? What you up to these days? Same old?
Well, same old. It's okay. It's going smoothly. No problems. As usual.
Nah, come on, man. Your as usual is many young folks sweet dream.
Well, to be honest, it's now it's hard to understand how things works these days. For example, WhatsApp developers tell, oh, our messenger is safe, but how do you know it's really safe? Well, the only way is reverse engineering and math.
That's why we have you.
cryptography.
You tell us.
Yeah. So because everybody tells our messenger is the best, our messenger or our social network or our application, our protocol is absolutely secure. Don't worry, it's the best protocol in the world. But in fact, various cases are possible.
We had a question for COS earlier today about you know COS, right? Dia, Mincifra, all those type of dramas.
Sure.
COS is here with us today. He opened the first day and we had a talk about Ukrainian cyber strategy, but there was a slightly related question, very interesting. I think you could address it. What do you think about Apple's plans to integrate the driver's license ID into their wallet? And what do you think? Is it a good idea?
To be honest, I'm an old fur. I'd say I'm an old fartosaur. And I do not like any innovations. This is my honest answer. But it doesn't mean the innovations are bad. And I think we will get something like that in a couple of years in any case. From Apple, not from Apple, from Google, maybe from some new company we never heard before. But we will get something like this. The world is moving to digitalization. And the world is moving very, very quickly. It makes me scared, but this is our reality. So if Apple is doing it, okay, let's Apple do it. If Apple changes its mind tomorrow, it will be doing by some other company.
Yeah. That's very, very along the lines of what I think about that, because we are old. Let's accept that at least.
Yeah.
So we don't like changes, but they are inevitable, and we have two choices: to keep up and to try to make those changes less harmful to everyone, just from our perspective. Yeah, so we know some stuff about that. Let's try to do something positive. Or we can not. And then we will just be left outside of the process. But from all companies, Apple certainly might be not the best to do it, but it's certainly somewhere in top 10, I would say. I mean, to do it correctly from second try.
Well, actually, I am looking at the Apple code every day, and I got something like a cognitive damage because of that. I I see a lot
So
of
what do you think
absolutely
about what I just
stupid
said? Is it
things.
complete bullshit or?
Well, we should say yes, they do great things sometimes, and sometimes they
And
do
let's leave it
some
at that.
crap. It's normal. That's normal. Yeah,
Yeah,
that's okay.
yeah.
So I can say, wow, Apple is doing it so cool, man. But from other point of view, I can say it's a total crap. It will not work. No, no, Apple
There's
is
no,
just doing it, and I believe they will be maybe not the first, but one of the first of companies who
yeah,
did it.
yeah. That's what I meant. I don't think that. No, I'm a long-term Apple fanboy. You know that, right? But that doesn't
Mhm.
affect my judgment about this. It's just a company that has complete supply chain from hardware to software to whatever, right? So they have complete control over it. That's the first one. And the second point is 1 billion iPhones. Okay. So with these numbers, you can do a lot of experimentation, like a lot.
Yeah,
And
yeah,
this can
yeah.
result on on large numbers. At large
Mhm.
number scale, it can result in something good coming out of it naturally, not because they intended, just because they have capability, you know,
Yeah, yeah,
like this.
yeah. I totally agree, actually. So anyway, the cyberpunk world predicted by, I don't know, Gibson, Batcat, and other cyberpunk wave writers is coming.
Mhm.
Is coming very quickly, and we should adopt. We should,
We should,
I don't know,
for
some
sure.
take it somehow, because yes,
Yeah, take it in somehow. You will have to. There is no way you can leave
there is no
in
way.
exile.
Nobody asks you. Yeah.
Yeah. Okay. So we finally have one question from the audience. Thank you very
Okay.
much. So Dima, where did you meet assembler implementations of DFA for the first time? So you recognize the structure.
Well, actually, from time to time, I see the obfuscation pattern like that. Probably, well, the earliest time I remember is it was probably the old people remember Star Force protection. It
We
was
do.
a quite popular protection.
We do.
Yes, yes, that protection for CD, you know, for that
Man,
for
this
CD,
is the
yeah.
conference that I have constant flashbacks. Right now, Oksana finished to talk about the gaming hacks, and yeah, I had some, and now Star Force. Cool, cool.
Star Force. So they did, I mean, the creators of Star Force protection did use something like that. Actually, the idea is not new, because deterministic finite automata are great for hiding code flow from static analysis. Static analysis literally, maybe not literally, but almost impossible. Dynamic analysis is harder, but possible. You saw that live demo with green and red addresses, where we actually see obfuscated calls in real time. So yes, it's possible, but it needs some efforts. You need to invest some time in this. I actually my choice of this piece of code was because it's simple. This piece of code is simple. It's not actually obfuscated quite hard. The mathematical model is simple. You saw that deterministic finite automata. It's absolutely simple. It's primitive from mathematical point of view. The code is quite primitive. That's why I can explain it in 15 minutes. Actually, that's because a harder, more complex, more sophisticated code needs more time to explain. Wow. So the answer is probably yes. Probably it's Star Force.
Yeah, yeah. Old times, good old times. So I have a question. So just
Yep.
from what I heard, from what I've seen, and for what we just discussed, if my memory doesn't fail me, yet. DFA is basically like second or third thing they teach you in discrete math, right? It's like first some very simple primitives, and then you get into it eventually into algorithmics and into compiler theory, right? So just in the middle of those topics, you got DFA because Turing, all that kind of stuff you have to learn before doing anything like fundamental. But they don't teach it to everyone. Not many coders, not many software engineers really know these basics nowadays, because they don't have to, right? They must not currently do that in order to produce high-level abstract code, right? So what do you need to, what background do you need to acquire before delving into such topics? Now, if you don't have that mathematical background, right? If you didn't have discrete math in the high school, in university.
Well, my answer may sounds strange, but actually you only need a very basic mathematical background. Because to be honest, preparing this presentation, I didn't remember the exact definition of DFA. Yes, I knew what DFA is, and I know what DFA is, but the exact definition with all its sets, etc., it was I didn't remember it. So I just opened a math guidebook I found in my bookshelf, open the definition, and if you understand, for example, what sets are, you can understand the definition of DFA in 2 minutes. So the only thing you really need is some very, very basic mathematical background. But if you are interested in making obfuscators, or you are interested in hiding your code from, research, from analysis, you probably should go further, and you probably should read some special articles, scientist papers, because actually making obfuscator and developing obfuscator techniques is a quite popular line of research in academia. Because just open Google Scholar and type DFA obfuscation, and you will get thousands of scientific papers. Because yes, people is doing it constantly, and it's a serious area in research, in math, in theoretical math. So if you want to do it, you can go forward, no problem. Everything is in Google.
So like very basic algebra, and I don't know.
You actually just need a set theory. If you learn set theory in the past, set theory and set theory and the first grade logic is your friend. All math are built on the set theory and first grade logic.
Yeah, sure. Thank you. So I think we will have one more question. We'll have two. So Dima, you wrote an ad hoc ASM tools functions. How do you make sure they don't have bugs? very, very practical question. How do you make sure they don't have bugs? I think I know the answer, but I bet it's harder than VBS code debugging.
Well, actually, the point here is I'm not a developer. To be honest, I am absolutely crappy developer, and my top level as a developer is proof of concept, usually created with Python or C++. So I am a researcher. I can reverse machine code. I can understand the machine code. Sometimes I think in machine codes after a long working day, but I can't write code. It's absolutely not my area of interest, and not my top skill totally. So I'm a researcher. I'm a reverse engineer, but I'm not a coder. So to be honest, I don't know how to create a secure code. I know how to find a vulnerability in a code. Yes, I know it. I know a lot of tricks how to do it, but I don't know how to to create a security code, especially if you are talking about binary security like stack, heap overflows, etc., etc. I don't know how to do it secure. I know how to find the bugs and how to turn it into vulnerabilities, but
thank you. I really don't know how to how to read the next question without our stream being downgraded to adult only. Okay, so can you please read it maybe in the chat?
Can
Not
you
allowed,
recommend...
of course.
Okay, that it's a question about that well-known programming language, Brain.
Not really well known, but yeah, it's
Brain
interesting.
Love. Let's call it Brain Love.
Brain Love, yeah, Brain Love, like an esoteric
Brain Love. Yeah, Brain Love
programming language that looks really nice. So it does not dissect any syntax or semantics from it. Just a fun exercise, as far as I remember, historically, right?
Yeah. Well, actually, the Brain Love language may look complex as source code. Yeah, the source code looks absolutely complex, but after translation into machine instructions, well, it doesn't look absolutely it doesn't look any complex, because it's just usual instructions from any usual programming language. By the way, I never see the Brain Love compiler, for example, for modern operation systems. I saw a Brain Love compiler for DOS, Microsoft DOS, and that was the top of their actually compiler career. I never saw a compiler for Windows, for example.
Now we have JavaScript. Why do we need Brain Love?
Yes, I totally agree.
Okay. So I think we can, if we don't have any other questions, we can wrap it up and let our speaker go free. Thank you very much. Thank you very much for the great talk and for nice and informative Q&A session.
Thank you. I thought it would be great to present some kind of bare bone reverse engineering talk on the conference. Well,
it's completely correct. Thank you for that. Thank you for your effort and for your insightful presentation.